paper titled Stochastic Data of multi environment. So if at how effectively is it and get some insight from we are planning algorithms in order to obtain a perfect prediction. So we took a case study of multiple drones to be swarming in an environment and be collecting some random data such as wind speed and wind direction, and we can use that data and present it to a machine learning algorithm and see how these machine learning algorithms will be able to predict, to make some predictions against the data we present to them and the way of which we present the in this paper we have a key problem to be addressed, which is to understand the data pattern of a random data, that is to understand how this data is changing over time and also how to cope up with those changes in order to present it effectively to a machine learning algorithms. And our proposed solution is that once we have a random data, we can tell the algorithm that this data is varying over time, and you need to prioritize some of these data in order to be able to make some good predictions against future events, which is known as the situation awareness, which is the process of understanding the data first and also how to make some predictions upon the data based on how you receive the data over time. So we can go to the next slide. So also, first of all, what is that stochastic data? In summary, we can say that any data that has these features may be regarded as a stochastic data. For example, it is changing over time, and at times it is a bit like looking at like random in nature, or we often find it very difficult to understand how it changes over time. And also it changes based on location and time. For example, a clear example of such types of data is like a wind speed and wind direction. And based on the location and the presence of mountains and the pages and so on. So we need to collect a relatively huge amount of data in order to be able to understand and make some predictions against future events, against like how the variables will be in near future. So in this paper, we are trying to show that it's very important to present your data to the machine learning algorithm in such a way that you can tell the algorithm that this sort of data are of recent, and the other part of data are a bit older. So you have to prioritize values from a recent data. So how can we achieve that? We can achieve that only by assigning probabilities and also maximizing the probabilities of the recent data over the older data. So by doing so, we found that the algorithms we use, that is the expectation maximization algorithms, perform better in terms of prediction than just presenting the data as usual to the machine learning algorithm without prioritizing part of the next slide. Can go to the next slide. So this we take Bayesian machine learning, which is I can see in the previous presenters present something about that. We have some conditional probabilities. We want to assigned to the variable. For example, if you see this equation, it is actually saying that the probability of A given V is equals to probability of B given A times probability of A all over probability of B. So once you collect your data from a machine, whether it is using drones or any form of data, you want to present it to the machine learning algorithm. So you are trying to tell the machine learning algorithms that what is the best prediction against near future events when I give you this data. So this is simply the explanation of this equation. Given the data, then what is the best future prediction against that data? So our own idea is that we have a recent data and older data, because we took a case study whereby the data is changing over time, which of course in real life situations, data often used to change over time. So we sampled wind speed and wind directions using drones. We simulated a forest and with mountains, and we used drones to collect huge amount of data and see how these data vary over time. So our own idea is to be prioritizing recent cases over older cases. This indirectly, we are trying to learn and unlearn some of this data. So most recent data have higher priority than older data. So giving them when you present them to the Bayesian learning algorithm, it will be weighting, based on our own efforts, it will be weighting out the recent data heavier than the older data. The previous slide, please. So then our probability will be in such a way that when we want to update the probability of every entry, we just normalize it and just assign a weight value. That is how we used to prioritize the recent cases. So let's say, for instance, we want to prioritize 80% of the data, then our weighting value will be 0.8, which means that the recent cases will be weighting like 180% than the older cases, than the rest of the 20%. So the choice of the weighting value is very difficult, because you want to be prioritizing some of this data over other data, unlike just presenting the data to the algorithms with recent with equal priority. So we have to be very careful in choosing our weighting factor. So this weighting factor value, we give it like just to be raising the difference of the time over like one value. Let's say, for instance, if it's changing after every minute, then you will say that your weighting value is 1, which is completely aligning the network. But if it's changing, let's say, for instance, after every 5 seconds, then you raise it over 5 and assign this percentage to your probability. So we found that this is just like a rule of thumb, I guess, but at least it is better than presenting the values directly to the algorithms, more especially the expectation maximization algorithm. The expectation maximization algorithm work as follows. It will just first use the Bayesian rules in this data in order to perfect its prediction. So once you prioritize the recent cases, so it's as if you are telling the algorithm that these recent cases, or 80% of this data, the recent data, is more important. So also, therefore, try to maximize its probability over the rest of the cases. So this the idea behind this is try to make the algorithm to be adaptable to the environment, because the data is changing over time. So also the algorithm will be following the mode of which the data is changing and trying to take more recent cases with higher priority than the older cases. Next slide. So in this, we simulated a forest on a space multi-agent simulation environment, and we took 4 drones and to be searching this environment and be collecting wind speed and wind direction over time. We assume that they have the sensor for detecting the wind speed and wind direction and reporting this data back to the base station. So we collect this data for a while and get some thousands of records and try to see how the expectation maximization took wind speed and wind direction because they exhibit the characteristic of stochastic data. Next slide. So this is how we collected our data. So we pay more attention only to the wind speed and wind direction. So each of the drones has a unique ID for each N3, and they will search through the forest. And in the previous slide, the yellow boundaries were fire, which present in the forest. And these fires are just to help up and see how wind is blowing. That is the rate of the movement of the fire at a particular direction and how the wind speed and wind direction is affecting it. As such, we can easily see the effect of the wind direction and wind speed because it is on simulation platform. So for instance, if the fire is moving toward the north direction, then we can easily conclude that, yeah, of course, the data reported by the drones is of course accurate and there is no any sensor error or noisy data. Next slide. So the process of the learning occur as explained on this flow chart. First of all, we will select the learning of algorithms, of which in our case is the expectation maximization algorithm I explained previously, in which that you present the data to the Bayesian belief network, which is the set of structure or a graph where you present your data using causal relationship, using not, for instance, wind direction is related to time, then you just draw an arrow and assign a causal relationship among these variables. So if you select your learning algorithm, first of all, you will compute the probability, that is the conditional probability using the Bayesian equation I explained previously. So you just submit this data to the network and try to iterate and maximize the accuracy of your prediction. So when the network make any wrong prediction, then you count that as error and normalize it to 1. So the network will be using what we usually known as the gambler's fallacy. For instance, if the agents are receiving wind direction towards north direction every 3 a.m., then they will maximize the probability. That is our own idea. They will maximize the probability by the weighting factor you submitted to the algorithm that during 3 o'clock, usually the wind direction blow in north direction. So when there's any changes, then the network will try to, the algorithm will try to adapt to these changes by iterating through the data and introducing the recent outlier variable and saying that, so this is a value, and the algorithm will now try to quickly maximize its probability idea we propose by weighting it higher in order to adapt to the changes in those data. Next slide. So in this result, we take, for instance, the wind direction and we sample it with and without the idea of weighting. So as you can see in the image B, we just present the data equally. So the network will, the machine learning algorithm will receive this data with equal priority and try to iterate through it and try to maximize these probabilities. So because the data is stochastic in nature, of course, we need to present a lot of data, which is more than 5,000 records and iterations in order to obtain some predictions. So our own idea, as you can see in image A, we're just trying to prioritize 80% of this data, and our prediction, our learning error reduces to 0. That is, we are trying to tell the network that unlearn all what you have learned in the previous 20% of the data and just concentrate on 80% of this data. Why? Because we see that the data is changing over time. So we try to define this weighting value in order to align the previous data that that is making the algorithm to behave in such a way that we don't like it, that it is not adapting to the changes in those data. So by introducing, that is by prioritizing 80% of this data, is as if as you are telling the expectation maximization learning algorithm that quickly concentrate on this portion of data and try to learn on it. So our own idea is to be learning and unlearning part of the data once you are dealing with stochastic data, because the previous approach is just to try to generate a lot of cases, a lot of data, which may need a lot of computational resources, and try to iterate through those data and maximize and your prediction accuracy by reducing the learning error rate. So our own idea is like try to unlearn those data that are misbehaving at a particular time. And also you can be able to reuse this data by just removing the weighting factor and idea we introduced. Next slide. So in conclusion, we are just trying to present a very idea that I'm trying to argue that while dealing with machine learning algorithms, instead of trying to generate huge amount of data and cases in order to present to the machine learning algorithms, we argue that you can also be able to unlearn the previous data and pay more attention on the recent data. So by doing so, you will reduce the error rate, you will also reduce the computational capacity, and you also make the machine learning algorithms more adaptable. As you can see from the Chris talk in the morning, once we want to generate a diagnostic system, we need to present huge amount of cases to the to our machine learning algorithms in order to be able to drive some prediction and inferences over it. So we argue that rather than presenting this huge amount of information, why not just try to make the machine learning algorithm adaptable to the data and try to pay some attention on the recent cases. For example, if you can see how we are dealing with COVID-19 pandemic now. So if you present all the symptoms cases to the machine learning algorithm and tell it that this is COVID-19, so it will adapt to the data that's saying that, yeah, these people are now suffering from a new virus of which I have to pay more attention on it, rather than trying to get a vast experience of all the data and trying to drive all the insight from it. So it will be like a context-based or a situation-based learning, rather than trying to learn and iterate. Because of course, even in real life situation, we used to learn something and trying to unlearn it over time. So this is our baby idea. Once you have a machine learning algorithms, you can be able to prioritize recent data, more especially when you are dealing with a stochastic random data. So if the data is not stochastic as well. So our own idea too will not work. That is one of its limitation. So in this work, we take only expectation maximization algorithms such as conjugate gradient descent.
Thank you very much, Saji, for the wonderful presentation. And we will get questions from the participants. And please, if you have questions for Saji or comments or contribution to the research, you can raise up your hand or you can post it in the chat room. We have a question already from John A. Say, thanks, Saji, good talk. When you talk about the problem of choosing weight in your data, win data by time, is there a flow to weight assigned to the data, or does the weighing tend to zero for older data? Also, are you weighing by time or by the number of data points collected? And those these allow for the inclusion of non-contiguous data. That is, if one UAV goes out of contact for a period of time. Outside of my research, I'm involved in, he continued by saying outside of his research, is involved in um, I'm involved in aviation and have some experience with some local geography affects low-level winds. So does your model include or account for topological data? And would it be possible to include this if it is not already? So Saji, a
Yeah.
question.
Uh, this is a very good question. Yeah, let me first start with the first question. Like in terms of selecting the weighting value for the win data over time. For now, as I explained earlier, is like we are only considering time. But my recent progress, I am trying to include how can we incorporate time, also the number of data and the number of iteration of the algorithms. So this is a very good question. For now, for instance, if we take the weighting value to be from 0 to 1, based on the suggestion on my research, we can say that if we use an equation 1 minus r raised to the power of change in time, so this is just a rule of thumb. This equation gives something better than just randomly choosing the weighting factor, of which it only consider a time. Of course, I agree with you. So when we are trying to deal with the number of data, also the iteration of the algorithms. So that R value in my previous research, I select it to be a number very close to 1, which can be which can also be approximated to 1. You can select it to 0.9 or 1. So I can see that if you take the logarithm value of the number of data and you multiply it with the number of iterations of the algorithms, so you can obtain the other value, which is better than also selecting it randomly. So this is just like a trial and error, but at least this equation gives something better than the previous context, of which we consider the number of data presented to the algorithms and number of iteration of the algorithms in addition to the time. Of course, it can be 0 when we keep seeing that the environment is not changing. When we say change in time, is that if the UAVs keep reporting values, not direction, we monitor that time. For instance, if they start started reporting it at 8 o'clock and they stop at 8:30 and change value, we can see that they change after 30 minutes. So we can take that difference, which is 30, and take it raised to the power of 1 and subtract it from 1, then try to normalize the outcome and see the weighting value we get. So it can be 0, of course, when it's go to like 0. Anything raised to the power of 0, I think is 1. So 1 minus 1 could be 0. So that value is 0, which is trying to tell the algorithm that now we are at the depot. Don't prioritize any part of the data. So in terms of the other UAVs, we assume that, of course, this is a very good question. We assume that our UAV are reporting accurate values, and they are using like swarm of UAVs to be reporting all of their variables to the sensor data. Of course, the expectation maximization algorithms allow you to model stuff like that. So we can regard that as our future work, that is trying to deal with the uncertainties and failure in terms of some UAVs and so on. So also, because I have issue with sharing my screen, I will have shown you how we collect the data using Bayesian belief network. Of course, the failure in sharing my screen has contributed, I think, a lot. But we use Bayesian belief network. Of course, it contains the topological situation, such as the mountains, the leeward site, and we consider all sort of stuff like that. And we model it using the Bayesian belief network and see how each of these events will affect the data we are trying to collect. So I can say, of course, it will, and in the future, we will try to dig deeper and present something more better than the current presentation. Thank you for the good question.
Thank you very much, Saji, for the response, and thanks, John A. He answered you. Excellent answer. Thanks. And so we'll wait for more questions. And if there is none, so we go on break, and we'll come back